This video is going to be an introduction to something called proof by induction. And there are a lot of moving parts in this technique. So it'll be really helpful if you could work on just the first problem from the in-class activities. Maybe not finish it, but get some of the ideas down. That'll make this video a lot easier to understand. The name of the file is Introduction to Induction. All right, now it may not at first glance seem that proof by induction has anything to do with sequences, but it actually does. So we're going to look at proof by induction, and the first thing we're going to do is sort of explore that connection with recursive sequences, recursively defined sequences. We're going to apply this recursive type of reasoning to a particular problem, and we're going to use that recursive reasoning to develop what we call proof by induction. All right, so remember from the old days not too long ago, like just the last video, right? What we would do is we would define the first few terms, like just the first term, a0 equals 5, and then we'd give some kind of recursive definition where an would be equal to some formula based upon the previous term. So in this case, you take the previous term and square it, and then add n to it. And that formula would work for n greater than or equal to 1. And we saw how the general idea behind defining sequences this way is we define the first term, we give a formula to tell how to get from one term to the next, and those rules alone, just by themselves, without actually saying what any of the other terms were explicitly, they allow us to compute all the terms of the sequence uniquely. We are actually going to use these same principles to prove theorems. So here's the problem that we're working on, and this is the first problem in the in-class activities that I asked you to look at before watching the video. So suppose you have a dot that is drawn on a huge plane, and you could think of that huge plane as it's a big table, right? So then we draw lines on the table so that they all go through that dot. The question is, if we draw n different lines, where n could be any natural number, how many regions do the lines split the plane into? Well, there's what we get when we draw one line in that you can see the little dot in the middle of that, and you can see there's a region on the left and a region on the right, so that's two regions. If we have two lines, you can see that there's a region in the upper left, lower right, upper right, lower left, that's four regions. And similarly, if you count for three lines, you can see that there are six regions. And we can sort of tell there's a pattern emerging here, right? So one would guess the answer is if you have n lines, then there are two n regions. Now, even though that guess is perfectly nice in terms of following a pattern, it doesn't really justify why that's going to be true all the time. So if we actually want to prove this is correct, what we want to do in this case is use recursion as a model. So what we do first is just verify the first case, which we actually already did. You draw one line, and you could literally see that we have two regions. So, and since we have two regions, we have n equals 1. 2 is the same as 2 times 1. That means the formula number of lines or number of regions equals 2 times n works. Then the next thing we're going to do is show how to get from one case to the next case. This is the part that's kind of like recursion, right? Recursive sequences, we use a formula to say how do we get from the last term to the current term that we're looking for. So in other words, how do we get that the result is true if we already know it, we just did it for n lines. How do we show that it's true for n plus 1 lines? And we're going to use the case of n lines to get to n plus 1 lines. Well, the first thing is I want to know what actually happens when I add a line. So if I have n lines, I have so many regions. What happens to the number of regions when I add a line? Well, here's what happens. When you add the line, it has to be between two existing lines because you're going through that same dot that all the other lines are going through. Now, on each side of that dot, before you get to the dot, for instance, you are going through what used to be one region, but then that line is going to turn that into two regions. And the same on the other side of the dot. Once you pass the dot, you're going to be in between two lines as well, and that single region is also going to turn into two. So that is two additional regions, right? Each of those times you make one region into two regions. You do that twice, that's two additional regions. Which means that each time a line is added, two more regions are created. So that's going to help us prove this. So we're going to show that the formula still works when we go from one step to the next. In other words, if the formula works for n equals k lines, it's also going to work for n equals k plus 1 lines. And what that means procedurally is we're essentially assuming that for k lines we have two k regions, because we're thinking of that as the case that we just did. And then we're going to show for k plus 1 lines we have 2 times k plus 1 regions, right? The number of lines multiplied by 2 gives us the number of regions. So let's try it. So if we have n equals k lines, we have 2 k regions. That's our assumption. And we also showed that when we added a line, then we add 2 extra regions. So if we have k plus 1 lines, we used to have 2 k regions, but now we got 2 additional regions, so that gives us 2k plus 2. If we simplify that by factoring out a 2, we get 2 times the quantity k plus 1. We get 2 times the quantity k plus 1 regions, which is exactly what we tried to show. Again, what this says is once we get to showing that it works for k lines, this process tells us that it also is going to work when we get to k plus 1 lines, sort of like we did for recursive sequences. So this is what we wanted to prove, so we're actually done. So here's the summary of how this thing works, right? First of all, you got to figure out what the answer to your problem is. One of the weaknesses of proof by induction is it doesn't tell you what the formula is or what the answer to your problem is. You kind of have to figure that out, and you can do that in any way, right? You can use any method. You can use blind guesses, right? So make sure you show that your answer is correct for the very first case, right? That's usually when n equals 1 if n is involved, right? Or perhaps for the first few cases. And this is very similar to what we do with recursively defined sequences, where we define the first terms. So maybe it's the first term that we have to define explicitly, or maybe it's the first 2 or 3, depending on what the recursive equation is like. Now you got to figure out what happens process-wise when you go from one case to the next. In other words, if you have k, if you understand n equals k, how do you get from that result to the result for n equals k plus 1? And I think of this as an intermediate step between the step we just did by checking the first few cases, that's called the base case, and the step that's going to be right after this one, which is called the inductive step. So what we're going to do is we're going to use our process from going from one case to the next to show that whatever it is that we think is true is going to be true for the n equals k plus 1 case. So we're going to assume the answer is correct for n equals k. We're thinking of that one as the one we just did. And we're going to show the answer is correct for n equals k plus 1. And then you're probably going to use the intermediate step above the process from getting from one to the next. So, and this is very much like the recursive formula in a recursively defined sequence. And if you put all those steps together, that method of proof is called proof by induction, and we're going to get a lot of practice doing that one. So for more, go ahead and see if you can finish the activities on the Introduction to Induction file that's included with this video, and then after that we'll work on some more.